We'll say more about this complexity class Sharpie in a minute on the next slide. For now, let me point out and remind you of this generic form of problems in NP, which have two parameters: the polynomial bound on the length of the witness in dependence on the length of the input, and the polynomial time decidable verifier V. And Cook-Levin theorem can be understood to mean that there exists an NP-complete problem, means there exists such a polynomial, and there exists a polynomial time decidable verifier, such that this problem is not just in NP, but even NP-complete. And for later purpose, when we talk about real complexity, it will turn out to be beneficial to record a strengthening of that theorem. Namely, there exists a polynomial time decidable verifier such that we can replace the polynomial here with actually the identity. That is, it's no loss of generality. We're interested in NP-complete problems to consider witnesses whose length is not just polynomially bounded in the binary length of the input, but whose length is actually bounded directly in the length of the input. That is, in this way. This will be used later when we investigate computational complexity of continuous problems over the reals. That's one thing. And then, as I already announced, I still owe you the introduction of this complexity class Sharpie. So what is Sharpie? Remember that NP is a class of polynomial time verifiable problem where the inputs are by definition are positive instances belong to the problem in NP if and only if there exists a witness of polynomial or linear length where being a witness can be decided in polynomial time. So when X belongs to the set, there exists at least one witness, and in general, there exist several witnesses. And a variant of this class NP is now the question not whether there exists such a witness, but how many of these witnesses there exist. Okay, and this exactly gives rise to this complexity class Sharpie. It counts the number of witnesses for Y for a given input X. We call these problems countable in polynomial time. And it's important to point out that this is a class of function problems, not a class of decision problems like P, NP, P space, and X, where the input is a natural number and the answer is yes, belongs to the set, or no, does not belong to the set. Instead, here, the input is a natural number and the output is another natural number, namely, the output is the cardinality, the number of witnesses to this input X. So how many such witnesses Y are there whose length is bounded polynomially in the length of the input, such that this pair witnesses that X belongs to the set. And this could be, for example, be the question, how many Hamiltonian circuits does a given graph have? So, which is of course a stronger question than asking, does the graph have a Hamiltonian circuit? Namely, if we know that the graph has like 17 Hamiltonian circuit, then we know that in particular that it has at least one Hamiltonian circuit, whereas the opposite is not true. If we only know that the graph has at least one Hamiltonian circuit, then we still don't know how many Hamiltonian circuits it has. So that intuitively, problems in Sharpie tend to be harder computationally, even more difficult than the problems in NP. And similar counting variants of decision problems in NP are, for example, the question, how many k clicks, how many clicks of size k does a given graph have? How many independent sets of size k does a graph have, and as I mentioned, how many Hamiltonian circuits does a graph have. So this is intuitively a larger complexity class with more difficult problems, or at least as difficult. But rigorously speaking, we cannot really compare the two complexity classes because NP is a class of decision problems and Sharpie is a class of counting problems. And the counting problem is not a decision problem, and the decision problem is not really a counting problem. And even more, comparing Sharpie with p-space, well, again, we can count in polynomial space by counting all witnesses. So we uh, like deciding NP problems in polynomial space, we can also solve counting problems in polynomial space by using a counter that counts whenever we try again all possible witnesses in polynomial space. And for each successful witness, we increase our counter. This will again take exponential time because there are exponentially many possible witnesses, but it will still be in polynomial space. And thus, every problem in Sharpie can also be solved in polynomial space. However, Sharpie is technically not a subclass of p-space because p-space only consists of decision problems. So this is a technical obstacle which can be made rigorous in several ways. Please, for this purpose of this lecture, let me be generous here and write that Sharpie is a complexity class between NP and p-space, although in rigorous sense this is not true. So this is a complexity class Sharpie that will also arise naturally when we investigate the computational complexity of numerical problems, in particular of Riemann integration. And finally, that's the last slide of this chapter. We need to talk a little bit about unary versions of these complexity classes. To this end, recall that all these decision and counting problems receive natural numbers, arbitrary natural numbers as input, and we measure the running time and the space, the memory used, independence not on the value of that input, but on the binary length of that input, right? So this is for your convenience, a reminder of the binary length. And we take the worst case time and space of all inputs of binary length less than n. And this is the definition of these complexity classes. But we'll also encounter restrictions of these complexity classes where the inputs are not arbitrary natural numbers, but only powers of 2, integer powers of 2. So here's a definition and abbreviation. This is a set of all natural numbers which are powers of 2, like 1, 2, 4, 8, 16, and so on. And so, for instance, 15 and 17 are not even permitted inputs to this the restricted decision problems that we will now introduce, namely subscript 1, and these classes indicate that we restrict the inputs to be only powers of 2. And intuitively, that makes the problem possibly easier. At least it doesn't make the problem harder, because an algorithm solving these restricted problems has only to deal with a restricted class family of inputs. So that possibly makes the problems easier. And so we have all these unary variants of P, of NP, of Sharpie, of p-space, and of X, where the inputs are restricted. So for example, for Sharpie, we only consider inputs that are power of 2. And again, we measure the running time independence on the length of the input, which, as you recall, is just So the length of 2 to the n by our very definition is n plus 1, right? With this rounding up and logarithm and all this stuff. That's easy to see. But I also need to point out that the witnesses for NP and for sharp P, NP asking whether there exists a witness and Sharpie asking how many witnesses there are. These are still arbitrary natural numbers, not only powers of 2. Otherwise, these problems are easily solvable in polynomial time because then there are only polynomially many witnesses that are powers of 2. But arbitrary natural numbers, that's the definition of the unary versions of these complexity classes. And we have the same hierarchy as previous for these unary classes, but comparing these unary classes to their full versions, that's a subtle point that goes beyond this lecture. I have introduced these classes because, again, they arise naturally in the context of problems over real numbers. So please keep this in mind when we return to that in the next. Now we want to talk a little bit about parameterized complexity. So traditionally we use n to denote our complexity parameter, the binary length of the given input, and we measure or count the time, the number of steps made in the worst case over all possible inputs of this given length n. And this gives rise to these complexity classes, for example, like P and NP, where we measure the computational cost to be like polynomial, then the decision problem belongs to P. And if there's a polynomial time verifiable witness, then we say the decision problem belongs to NP. And here's an example such decision problem like the it's called edge cover problem, where the input is a given graph and an integer parameter k, and the decision problem is to decide whether there exists a subset of the edges of this graph such that every vertex is adjacent to at least one of these edges. So originally, this is optimization problem, find a smallest such subset f of edges that in a sense cover all vertices in the sense that every vertex is adjacent to at least one of these small subset of edges. And this has been converted into a decision problem where we ask, given a parameter k, whether there exists a subset of size k. So here's two example instances, two graphs. The left graph has 7 edges, and the right graph has 6 edges, and the left graph has an edge cover of size 3, namely the edges indicated here in red cover the vertices. Every vertex is adjacent to at least one of the edges that are drawn here. So this graph has an edge cover of size 3. So if the input is this graph together with a parameter k equals 3, then the answer would be yes, there exists an edge cover of size 3. If the parameter k is 2, then the answer would be no, because there is no edge cover of size 2 of this graph. And if the input is 4, then still the answer is yes, because there's an edge cover of size 3, then there also is an edge cover of size 4, obviously. For the graph on the right, this edge cover of size 4 is optimal. There is no edge cover of size 3. So superficially, this again looks like our typical NP problem. Here, the input is the graph, vertex, vertices, edges, and the parameter k encoded in binary. And we ask whether there exists such a subset of the edges. And this also immediately can serve as a witness, namely given a subset of the edges it is easy to verify whether this subset has the given required size k and whether it covers all vertices. And naively, it seems like we might need to try all possible subsets of edges of size k, of which there are n choose k many, which is exponential in n if k is like n over 2, for example. It would be exponential, but there is actually a polynomial time algorithm. So superficially, this looks like an NP problem, but it is there's a polynomial time algorithm. Namely, the algorithm proceeds as follows. First, compute a maximum matching using one of the standard graph algorithms, and then greedily extend that um, such that every vertex is adjacent to an edge. And one can see that this is indeed a minimum edge cover. So this is a polynomial time decidable problem. It's can improve our complexity classification from NP to P for the edge cover problem. This is an effect similar to the Eulerian cycle versus the Hamiltonian cycle problem. Namely, also here we have a situation where minor modification of the problem, switching from edge cover to vertex cover, suddenly makes the problem harder. Namely, vertex cover is kind of like a dual problem. Again, the input is a graph and a natural number parameter k. But now the question is whether there exists a subset of the vertices that cover the edges rather than a subset of the edges that cover the vertices. And this subset of the vertices to cover the edges means that every edge must be adjacent to at least one of the small subset of vertices. So here's again, for illustration purposes, two example instances. So here is our graph from the right hand to basically again. And this has a vertex cover of size 2. The two vertices marked red cover all edges. Every edge is adjacent to at least one of the two red vertices. And this is obviously the smallest possible vertex cover that this graph admits, because no vertex set of size 1 can cover all edges. And this is also, again, the same graph as here. And this has a vertex cover of size 3. The three red vertices cover every possible edge. And again, I leave it to you to verify that there is no vertex cover of size 2. So this is a vertex cover problem. Again, this is a typical example of an NP problem where now the witness is the vertex cover, a witness of polynomial size, which is easy to verify whether it's a vertex cover or not. But unlike the edge cover problem, it doesn't seem like there's a polynomial time algorithm for the vertex cover problem. And in effect, one can show that the vertex cover is an NP complete problem. So one of these problems that if there were, or if there is a polynomial time algorithm solving it, then all problems in NP collapse to be polynomial time decidable, like the clique or the independent set problem, Hamiltonian cycle problem, and so on. So most likely this problem cannot be solved deterministic polynomial time. But so it's NP complete. The C stands for NP complete. We cannot hope to solve this in polynomial time, but there is a relatively efficient algorithm. So in the worst case, it takes exponential time, right? But the worst case is the case where k, the size of the vertex cover, which we're interested in, is roughly n over 2, right? Because then we have to, a naive algorithm trying all vertex covers would need to search an exponential space of candidate vertex covers. But there's an algorithm whose running time has this form. It's polynomial in n times exponentially in k. Now, as I said, we cannot hope for anything less than exponential, but when k is small, this is a efficient algorithm, right? So when n is large and k is small, then this term governs kind of the asymptotics. And this is kind of like a constant, large, but a constant. So this algorithm is an example of a algorithm, or this problem is an example problem of this famous complexity class FPT, fixed parameter tractable, which means that it admits an algorithmic solution which is polynomial in the input size n times some arbitrary, in this case exponential, but function in a secondary parameter which may or may not be small. And so for small values of this secondary parameter k, this is a efficient algorithm. And this distinguishes vertex cover from other problems. So other problems may not be fixed parameter tractable. They may not admit such an algorithm with such a decomposition of its running time into a polynomial part times an exponential part, depending only on some parameter k and not on the input size itself. This is a class FPT of fixed parameter tractable problem, and we call n the input length, the primary cost parameter, and k the secondary cost parameter. What we choose or use to denote with k depends on the problem, what we choose as secondary parameter. And we're introducing or recalling this parameterized complexity theory because it will arise again when we talk about real complexity theory in chapter 5. Finally, let us also recall average case complexity, which is a refinement or counterpart to the worst case complexity theory that we all have become familiar with. So to motivate this, recall the famous quicksort, which has its name because it is such quicker sorting algorithm. But as you may recall from introduction to algorithms, actually this is not so efficient algorithm in the worst case, at least when using a naive approach to choosing the pivot for splitting the input, namely when just taking the first, or also if we just take the last element as pivot for splitting the input, then on when the input actually is already sorted, then quicksort boils down to quadratic running time and therefore is as bad as bubble sort. And of course that not only applies to sorted inputs, but to other inputs as well, but not really to many inputs, as you can easily verify using experiments. So only in the worst case, this naive approach or implementation of quicksort has a bad quadratic running time, but these are rare inputs. And in what sense are they rare? Can we formalize this? And indeed, one can. There's a this is called the average case analysis of quicksort, classical topic. Namely, whenever the input is chosen randomly, input of size n is chosen randomly among all n factorial many permutations, many possible inputs of size n, then the expected number of comparisons performed by quicksort, which is a good estimate of its actual total number of steps, its total running time, is bounded by 2 times n times the natural logarithm of n. I won't prove this theorem, but quoting this here, which, because it's a formalization of the intuition and experimental evidence that on average, quicksort is pretty quick, has this running time n log n, which we know is optimal, but here it's only attained in expected value because since we're talking about random inputs, the number of operations, the running time of quicksort is a random variable. It depends not just on the input size n, but also on which input permutation is presented to process. So therefore, it makes sense and actually is required to talk about expected value of this random variable. The expected running time is n log n is optimal, but there's still these worst cases, but these worst cases are sufficiently rare so as to not really affect or increase the expected running time beyond the optimal asymptotic n log n. And also let me point out that here we refer to a probability distribution on all inputs of size n. Well, for arrays, it's maybe reasonable to consider the uniform, the equiprobable distribution among all possible inputs of size n. But when we want to kind of generalize this to a complexity theory, so we want to consider this example of a quicksort as a prototype example of a general complexity theory of average case complexity, then we're faced with the question, what probability distribution should we use there? For example, for decision problems as a subset of, let's say, natural numbers, what probability distribution should we consider among the natural numbers as the set of possible input instances? It's not really canonical which probability distribution to consider in natural numbers, because unlike in this case, there are finitely many possible inputs of size n, so we can define all of them to be equally likely, but the set of natural numbers is infinite, so we cannot define all natural numbers to be equally likely. The probability must somehow decay as the natural numbers tend to infinity, and it's not at all clear that it's a question of definition, not a mathematical problem, but a question of how to define canonical probability distribution. And Leonid Levin, one of the two guys who invented complexity class NP, actually introduced average case version of the complexity class NP, which he called dist NP. So this is an average case version of NP, a class of decision problems which can be solved efficiently or not efficiently in deterministic or non-deterministic polynomial time, but this class, that problems comprising this class, must be equipped with a probability distribution. So, as I said, there's not one canonical probability distribution on the natural numbers. Instead, the probability distribution is part of the input or it's part of the problem. So problem in this class is a pair, a decision problem, and a distribution on the instances of this decision problem. And I'm keep stressing this because it will turn out when we talk about average case real complexity that over the reals, there is a canonical probability distribution, at least on the real unit interval. For example, there's the Lebesgue measure, the equidistribution, although the real unit interval has infinitely many, uncountably many elements. The Lebesgue measure is, of course, a canonical distribution there. And maybe on the entire real line, one can consider the Gaussian distribution as a canonical distribution. So to summarize, yes, in the real setting, actually, Many of these concepts will appear again, and arguably more canonically and more naturally than in the discrete setting. So we all know about expected cost, which seems like a great candidate for average case complexity, namely the expected cost of the algorithm A on input X, where the expectation refers to all inputs of length n with respect to the distribution, probability distribution D on the inputs of length n. But the question is, how could we define polynomial average case complexity? So this is a quantitative expected or average case runtime, but what is this polynomial average case runtime? And maybe a naive way is to proceed from polynomial worst case complexity, which can be expressed in this way. So for all inputs length n, the maximum, that is the worst case runtime of the algorithm A on input X, where X has length up to n, must be bounded by a polynomial, that is by some expression of k times n to the k, where k is some integer. Here we combine the exponent of the polynomial and the coefficient into one integer constant without loss of generality. And from there, it may seem natural to define polynomial average case complexity similarly by saying that the expected cost of the algorithm on all inputs of length up to n with respect to that distribution must be polynomial, that is bounded by k times n to the k for some integer constant k, right? So expected polynomial. However, this definition violates some important structural properties, and therefore is not suitable. More precisely, consider this example. Consider an algorithm which, for some reason, artificial algorithm on the input of length n, which consists only of zeros, has exponential time, exponential many steps. Why? I don't care, but anyway, let's just suppose such an algorithm, whereas for all non-zero inputs, it has like linear cost. All non-linear zero inputs of length n, it has linear cost. Then if you calculate the average cost of that algorithm with respect to the uniform distribution, let's say all inputs of length n are equally likely, then this exponential contribution is very unlikely, right? It's just one of exponentially many of 2 to the n inputs of length n, whereas the majority of the inputs, all other, have linear. So in total, that means this algorithm has polynomial, even has linear expected cost. But now let's suppose that we apply some polynomial time reduction, some transformation to the algorithm, which, for example, in this increases n twofold, right? So increase some reduction, which artificially maybe appends or repeats the input string to make it having length 2 times n. Then here the running time becomes 2 times n, which is still linear, which is good. But here the running time now becomes 4 to the n, right? And 4 to the n now does not anymore cancel against the probability for such a bad input to occur, which is still 2 to the n. So that suddenly, after this polynomial reduction, the same algorithm suddenly has an exponential average case cost. So this is demonstrating that this definition of polynomial average case complexity is not robust. It's not closed under, let's say, for example, quadratic slowdown, quadratic reduction, and therefore it's not a good definition, right? In order to find a better definition, let's look at the following equivalent reformulation of the polynomial worst case, namely we kind of solve this or manipulate this expression. Instead of taking the running time bounded by k times n to the k, we take the k's root of the running time, right? That is then bounded by the k's root of k times n, right? N outside of the root, and we divide that by n. So then this is equivalent to saying that the kth root of the running time over all inputs of length n divided by n is bounded by some constant. And again, it's no loss of generality to have the same constant for the root and for the bound, possible different constant than here. So this is an equivalent reformulation. And now based on that reformulation, we can turn that into an average case cost estimate by saying that by requiring that the expected running time taken to the k's root over all inputs of length up to n divided by n should be bounded by a constant. So this is another candidate definition which differs from this definition, and this latter is actually the definition that Leonid Levin proposed. So to summarize, the naive definition for average case polynomial cost is not robust, but this definition is not hard to see that this one is robust under polynomial reduction, and this is the definition used since then for to define polynomial average case complexity and classes. Okay, so moving on to a new topic, let us recall what we talked about reductions between decision problems. Maybe what we covered is nowadays called a CARP reduction. Reduction, or also called a many-one reduction, where the algorithm supposed to solve the decision problem A can use the decision problem B in the reduction using the reduction function, and that basically means the algorithm receives the input question or instance for problem A, processes that according to the reduction, then queries whether the result of the reduction belongs to problem B using the hypothetical algorithm for that, and then uses that directly as answer. That's the definition of many-one reduction, that whether the transformed instance belongs to B is by very definition must be the answer to the question whether the original instance belongs to A. Now, there are variants of this reduction. So like logarithmic space reduction, where the reduction function is required to not be just polynomial time computable, but even log space computable. So that's a stronger condition. That's a finer notion of reduction, log space reduction, many-one reduction. A different kind of generalization is not many-one reduction, but Turing reduction. This is technically the notion introduced by Stephen Cook in 1971. In Turing reduction, the algorithm similarly retrieves the input, but now instead of querying, it can query the transformed instance, but now it gets a chance here to fill this white space and to use and to transform the answer to that query, not just pass on the answer to the query directly as answer to the original question, but may make some additional computations before presenting the answer. So that's a difference between many-one also called carb reduction on the one hand, and Turing reductions on the other hand. The difference is whether the algorithm is allowed to process the answer and, for example, invert the answer, right? So, for example, the holding problem cannot be reduced to its complement, as we know, using many-one reduction. But using Turing reduction, that's pretty easy. Just make a query and then flip the answer provided by the query. There's another version. So this is called Turing reduction with one query. There's a variant where the algorithm can make several queries to the other decision problem B. So that algorithm is allowed to make kind of a loop here, repeatedly query, process the answer, and possibly the input to come up with another query adaptively and make another query and so on. So this is well permitted in Turing reduction. And now we want to discuss some further variants of this reductions graphically. So the original notion of carb reduction or many-one reduction is about the question whether given input x belongs to A, and the reduction function f transforms that into an instance y for the problem B, and then queries whether this y belongs to B, and then the answer to that query must also be the answer to the original question. That's the standard many-one carb reduction. And the reduction function must be computable in polynomial time. If we consider log space reduction, then the reduction function must be log space computable. Polynomial time Turing reduction, on the other hand, is allowed to process the answer. That means instead of directly passing the answer of the query to the answer of the original question, now the algorithm gets to process that answer and then only needs to present the thus calculated answer to the original question. And for repeated Turing reductions, the algorithm can repeat that process, can cycle, can process the answers to come up with new queries. You see here y prime repeatedly, as long as that happens only a polynomial number of times. And that picture is, or perspective is actually helpful, since for now when we want to talk about reductions between function problems. So before, everything was about decision problems. The answer was always yes or no, and there were various possible inputs like integers, but the answer was only one bit. But when we want to talk about reductions between function problems, where both the argument and the value is a natural number, then there's some additional variations that will be later of relevance when we talk about reductions between real problems, which also excludes decision problems. Any decision problem over the reals is trivial, as you call. So let's consider reductions between functions in a similar setting. So now instead of a yes-no question, where the answer is yes or no, we want to calculate the value of an integer function a of x, right? So decision problem, does it belong to a, yes or no? Function problem, what is the value of a of x on input x? And so the same kind of reductions applies to this case. Now the oracle, the B, is again not a decision problem, yes, no answer, but a function problem. And so the result of this oracle query is not yes, no, but it's another value z, which may either be presented directly as the result of the original question, what is a of x? That's kind of the many-one reduction case. Or the Turing reduction case between function is that now the um, output, the result of the query, can actually be processed further, right? So this is direct answer, and this is further processing, possibly processing together with the input, so that the input can be, original input can be used several times for the query and for the further processing, or it can not be used. It can be used only once for the to make up the query, and then only the answer of the original query can be used to calculate the final value. And this very subtle differences in discrete reduction between discrete functions actually becomes relevant when later we talk about reductions between continuous, between real functions. Okay, and as usual, the discrete reduction must be possible in polynomial time. And again, we have these two variants where the answer can, only one query can be made and then process the answer to produce the output, or several queries repeatedly and adaptively can be made. So the latter, when the original input can be used both for the query and for further processing. This is formalized like here. So here now we have two transformations into the reduction. The first transformation, F, transforms the original input X and then passes that to the oracle B. And then there's a second transformation that uses the answer of the oracle query plus the original input. And this additional transformation is captured by a polynomial or log space computable function G, which now has two arguments, whereas the case where the original argument can be used only once to make the query, and then the result of the oracle query can be processed, but not using the original input anymore here. This is called strong reduction, strong Turing reduction. So this is Turing reduction between functions. This is strong Turing reduction between functions. For Turing reduction between functions, there are two transformations. For strong Turing reduction between functions, there are also two transformations. And the difference is that in the first case, the original argument, x, an integer, is available to the second part of the transformation, whereas in this case, it's not. Okay, so that's all about our chapter 4 on discrete complexity. First, we talked about classical discrete complexity, computation with cost, computational complexity of arithmetic like addition and multiplication and division. We recalled several complexity classes such as P, NP, short P, and P space. And we've classified example decision problems according to these complexity classes. And we've compared decision problems using our standard, which we now know to be called many-one or CARP polynomial time reduction, and arrived at the complexity class picture with these complexity classes. In this second part, advanced complexity, we would proceed from that complexity class picture to introduce this new counting complexity class, which is a complexity class of functions. We talked about unary complexity classes, where the inputs are restricted to be integer powers of 2 only. We talked about parameterized complexity, where we measure computational cost in the dependence on the binary integer length, and in addition, independence on some other parameter. And in particular, we defined fixed parameter complexity. We talked about average case complexity according to Leverin, computational complexity considered in the expected case with respect to some certain probability distribution on the inputs. And we saw that the naive definition is not robust under, let's say, polynomial reductions, which led Leonid Levin to consider this alternative definition with taking the kth root for some constant k. And then we discuss some further variations of reductions like log space reduction, Turing reduction between decision problems, and similar reductions between function problems where the variance depend on what is the computational power of the transformation or the transformations. Several transformations are employed when we talk about reduction between function problems, such as short p functions, and whether it's possible to process the answer to the Oracle query, and how often this can be processed. So that's all for today. Thanks for your attention, and we'll meet again when we talk about chapter 5 on real complexity theory. Thank you.